Okay, so we did one Hess's law problem there, and we want to look at another Hess's law problem here. So, as I mentioned in the previous video, there's one issue here that is going to be important to recognize when we're going through a Hess's law type calculation. Now, again, based on the information provided or what the problem looks like, we should be able to identify it as a Hess's law problem, as opposed to the problem where we are just using the enthalpy in terms of dimensional analysis or unit conversion type of calculation. So if we look just at this problem, we want to calculate the enthalpy change for this reaction. There's our target reaction, and we're given a bank of known reactions. So what we need to do is take the bank and use it to build up the target reaction that we're provided. So we're going to start with 1 mole of NO gas, and here it is in this first reaction. It's on the correct side. It's a reactant. It's 1 mole. It's the right phase. Perfect. So I'm going to use that reaction. NO gas plus O3 is ozone, and that makes NO2 and O2 gas. Now, I'll use a similar system here. I was trying to find NO. I found it right there. Now, one thing to notice here, NO2 gas is our product, 1 mole of it. And we got that from this reaction as well. So we've actually introduced one of the reactants and one of the products in our target reaction already, just by using that first reaction. And we wrote it exactly as it was in the bank. So the enthalpy that we may use once we've figured out how to add up and get our target is the same there as well. Now, the other component here that we want is an oxygen atom, just O, in the gas phase. So if we find that down here, we have O2 gas going to 2O gas. Perfect. So that's what we want, O gas. Now, in this reaction, in the table, it's the product, and there's 2 moles of it. Now, we only want 1 mole, and we want it to be a reactant, so we can do 2 things there. First, we're going to cut the quantities in half, and second, we're going to flip-flop the reaction. So I'm going to flip-flop it so that oxygen atom is my reactant, so just one oxygen atom as a gas would make 1/2 of an O2 molecule in the gas phase. Now, I've got to take both of those changes into effect when I transfer the enthalpy to the reaction I'm using here in my Hess's law problem. I cut it in half. That means I want to divide this by 2, but I also turned the reaction around, and that would make this negative. So the enthalpy that would go here would be negative 495 divided by 2. Now, it's up to you. If you want to divide it by 2 first and write that in, that is fine. I kind of, just for clarity purposes, I like to show it this way to kind of show what I'm doing. I cut that reaction in half. I'm cutting the quantity in half as well, right? So if you have half the material, you're only going to get half of the energy change associated with that. Now, O, there is my other component of my target reaction. So with that, I've got all the pieces of my target reaction. But what's different about this problem, and the reason that I have it here as a second example, is if we were to combine these 2 reactions now, we would get the pieces in our target reaction, but we would not cancel out everything else that's present. We'd have ozone as a reactant, and we'd have 1.5 moles of O2, or molecular oxygen, as a product. So that's not just the target reaction we're looking for. There are other things going on. So in this case, we need to add a third reaction to try to cancel out those extra pieces that are still there. So I need an ozone on the product side to cancel this one on the reactant side, and I need 1.5 molecular oxygens on the reactant side to cancel these on the product side. So that reaction is part of the bank that we have here. We just need to flip it. We need to flip it the other way. So I'm going to flip that reaction, but the quantities are fine. 3/2 O2 molecules becoming an ozone molecule. And if that's negative up there in the table, it's going to be positive down here since I flipped reactants and products. Now, what that does is it cancels out the things I want to cancel out. I've got 1 mole of ozone here as a reactant, 1 here as a product. So when I combine these 3 reactions, that will disappear from my overall equation. 3/2, that's 1.5 moles of O2. There's a half, there's a whole. So all the O2 cancels out, and that gives me the exact reaction I'm looking for. 1 mole of NO plus an oxygen atom gives me the product of NO2 gas. Now, like Hess's law says, if I can combine these reactions to produce my target reaction, then combining their enthalpies will give me the enthalpy. Just make sure you do all the things you need to here, like dividing by 2, getting the signs correct. Okay. All right, so I'm going to again start with the positives and then subtract the ones that are listed as negative. Nope. Well, let's do 495 divided by 2 first. So I don't have to add that in. That would be 247.5, and that's negative. So 142.3 minus 247.5 minus 198.9. So that gives me a total of negative 304.1 kilojoules. That would be the enthalpy for this particular reaction. Now, significant figure-wise, the enthalpy here for the oxygen breaking apart reaction really did only go to the ones place. So it may be better to round this to 304 based on that. Significant figures there in that one enthalpy. That might limit us to the ones place down here when we add these up. Not a big deal there one way or another. Okay? But the basic idea here is putting together all the pieces in the Hess's law problem. So again, think about how do I recognize what type of problem I'm looking at, and then what do I need to do once I've recognized? Is it just the enthalpy and how I'm applying it to an amount, or is it Hess's law where I'm trying to identify that target reaction and put it together? Now let me just introduce, it's at the bottom of the page here, the third type of enthalpy problem is again a little different. So there's another way we can think about enthalpy, and this is called the standard enthalpy of formation. So again, the little degree sign means standard or standard conditions, and the subscript F here is for formation. So this is not for a reaction, this is for an individual molecule or compound. This is the enthalpy change for the formation of 1 mole of a compound directly from its component elements in their standard states. So there's an enthalpy we can associate with any material and its phase that would tell us how much would it cost energy-wise to produce that material if we started from the elemental versions of the constituent atoms. Okay? Now, if we can find this information for the components of an equation, and we can, there's a nice table in the back of the book that has all of this information. If we can find these enthalpies of formation, we can combine them to calculate the enthalpy change for a reaction. So here's an equation that we're going to use, and this is an equation that you, again, should be familiar with because you'll want to be able to apply it when we find a problem like this, say on an exam. The enthalpy change for the entire reaction is equal to the sum, so there's a capital sigma here, is we're summing up these quantities. So it's the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So given an equation, if we look all those values up, we really just need to then combine them, along with how many moles of each are part of the reaction, into this equation, and that will give us what the overall enthalpy change for the reaction is. So we'll practice a couple of those, but as we flip the page, we'll flip over into the next video.